Saturn is the sixth planet from the Sun and the second largest in the solar system, after Jupiter. It is a gas giant with an average radius of about 9 times that of Earth. It has an eighth the average density of Earth, but is over 95 times more massive. Even though Saturn is almost as big as Jupiter, Saturn has less than a third the mass of Jupiter. Saturn orbits the Sun at a distance of 9.59 AU, which is about 1,434 million kilometers, with an orbital period of 29.45 years. Physical characteristics. Saturn is a gas giant, composed predominantly of hydrogen and helium. It lacks a definite surface, though it is likely to have a solid core. The planet's rotation makes it an oblate spheroid, a ball flattened at the poles and bulging at the equator. Its equatorial radius is more than 10% larger than the polar radius, 60,268 kilometers versus 54,364 kilometers. Jupiter, Uranus, and Neptune, the other giant planets in the solar system, are less oblate. The combination of the bulge and the rotation rate means that the effective surface gravity along the equator, 8.96 meters per second squared, is 74% of what it is at the poles and is lower than the surface gravity of Earth. However, the equatorial escape velocity, nearly 36 kilometers per second, is much higher than that of Earth. Saturn is the only planet of the solar system that is less dense than water, about 30% less. Although Saturn's core is considerably denser than water, the average specific density of the planet is 0.69 grams per cubic centimeter because of the atmosphere. Jupiter has 318 times Earth's mass, and Saturn is 95 times Earth's mass. Together, Jupiter and Saturn hold 92% of the total planetary mass in the solar system. Internal structure. Despite consisting mostly of hydrogen and helium, most of Saturn's mass is not in the gas phase, because hydrogen becomes a non-ideal liquid when the density is above 0.01 grams per cubic centimeter, which is reached at a radius containing 99.9% of Saturn's mass. The temperature, pressure, and density inside Saturn all rise steadily toward the core, which causes hydrogen to be a metal in the deeper layers. Standard planetary models suggest that the interior of Saturn is similar to that of Jupiter, having a small rocky core surrounded by hydrogen and helium, with trace amounts of various volatiles. Analysis of the distortion shows that Saturn is substantially more centrally condensed than Jupiter, and therefore contains much more material denser than hydrogen near its center. Saturn's central regions are about 50% hydrogen by mass, and Jupiter's are about 67% hydrogen. This core is similar in composition to Earth, but is more dense. The examination of Saturn's gravitational moment, in combination with physical models of the interior, has allowed constraints to be placed on the mass of Saturn's core. In 2004, scientists estimated that the core must be 9 to 22 times the mass of Earth, which corresponds to a diameter of about 25,000 kilometers. However, measurements of Saturn's rings suggest a much more diffuse core, with a mass equal to about 17 Earths, and a radius equal to about 60% of Saturn's entire radius. This is surrounded by a thicker, liquid metallic hydrogen layer, followed by a liquid layer of helium-saturated molecular hydrogen, which gradually transitions to a gas as altitude increases. The outermost layer spans about 1,000 kilometers and consists of gas. Saturn has a hot interior, reaching 11,700 degrees Celsius at its core, and radiates 2.5 times more energy into space than it receives from the Sun. Jupiter's thermal energy is generated by the Kelvin-Helmholtz mechanism of slow gravitational compression, but such a process alone may not be sufficient to explain heat production for Saturn because it is less massive. An alternative or additional mechanism may be the generation of heat through the raining out of droplets of helium deep in Saturn's interior. As the droplets descend through the lower density hydrogen, the process releases heat by friction and leaves Saturn's outer layers depleted of helium. These descending droplets may have accumulated into a helium shell surrounding the core. Rainfalls of diamonds have been suggested to occur within Saturn, as well as in Jupiter, and ice giants Uranus and Neptune. Atmosphere. The outer atmosphere of Saturn contains 96.3% molecular hydrogen and 3.25% helium by volume. The proportion of helium is significantly deficient compared to the abundance of this element in the Sun. The quantity of elements heavier than helium, known as metallicity, is not known precisely, but the proportions are assumed to match the primordial abundances from the formation of the solar system. The total mass of these heavier elements is estimated to be 19 to 31 times the mass of Earth, with a significant fraction located in Saturn's core region. Trace amounts of ammonia, acetylene, ethane, propane, phosphine, and methane have been detected in Saturn's atmosphere. The upper clouds are composed of ammonia crystals, while the lower-level clouds appear to consist of either ammonium hydrosulfide or water. Ultraviolet radiation from the sun causes methane photolysis in the upper atmosphere, leading to a series of hydrocarbon chemical reactions, with the resulting products being carried downward by eddies and diffusion. This photochemical cycle is modulated by Saturn's annual seasonal cycle. Cassini observed a series of cloud features found in northern latitudes, nicknamed the String of Pearls. These features are cloud clearings that reside in deeper cloud layers. Saturn's atmosphere exhibits a banded pattern similar to Jupiter's, but Saturn's bands are much fainter and are much wider near the equator. The nomenclature used to describe these bands is the same as on Jupiter. Saturn's finer cloud patterns were not observed until the flybys of the Voyager spacecraft during the 1980s. Since then, Earth-based telescopy has improved to the point where regular observations can be made. The composition of the clouds varies with depth and increasing pressure. In the upper cloud layers, with temperatures in the range of 100 to 160 Kelvin and pressures extending between 0.5 to 2 bar, the clouds consist of ammonia ice. Water ice clouds begin at a level where the pressure is about 2.5 bar and extend down to 9.5 bar, where temperatures range from 185 to 270 Kelvin. Intermixed in this layer is a band of ammonium hydrosulfide ice, lying in the pressure range 3 to 6 bar with temperatures of 190 to 235 Kelvin. Finally, the lower layers, where pressures are between 10 and 20 bar and temperatures are 270 to 330 Kelvin, contain a region of water droplets with ammonia in aqueous solution. Saturn's usually bland atmosphere occasionally exhibits long-lived ovals and other features common on Jupiter. In 1990, the Hubble Space Telescope imaged an enormous white cloud near Saturn's equator that was not present during the Voyager encounters, and in 1994 another smaller storm was observed. The 1990 storm was an example of a great white spot, a short-lived phenomenon that occurs once every Saturnian year, roughly every 30 Earth years, around the time of the Northern Hemisphere's summer solstice. Previous great white spots were observed in 1876, 1903, 1933, and 1960, with the 1933 storm being the best observed. The latest giant storm was observed in 2010. In 2015, researchers used the Very Large Array Telescope to study Saturnian atmosphere and reported that they found long-lasting signatures of all mid-latitude giant storms, a mixture of equatorial storms up to hundreds of years old, and potentially an unreported older storm at 70 degrees north. The winds on Saturn are the second fastest among the solar system's planets, after Neptune's. Voyager data indicate peak easterly winds of 500 meters per second, or 1,800 kilometers per hour. In images from the Cassini spacecraft during 2007, Saturn's northern hemisphere displayed a bright blue hue, similar to Uranus. The color was most likely caused by Rayleigh scattering. Thermography has shown that Saturn's south pole has a warm polar vortex, the only known example of such a phenomenon in the solar system. Whereas temperatures on Saturn are normally minus 185 degrees Celsius, temperatures on the vortex often reach as high as minus 122 degrees Celsius, suspected to be the warmest spot on Saturn. A persisting hexagonal wave pattern around the north polar vortex in the atmosphere at about 78 degrees north was first noted in the Voyager images. The sides of the hexagon are each about 14,500 kilometers long, which is longer than the diameter of the Earth. The entire structure rotates with a period of 10 hours, 39 minutes, 24 seconds, the same period as that of the planet's radio emissions, which is assumed to be equal to the period of rotation of Saturn's interior. The hexagonal feature does not shift in longitude like the other clouds in the visible atmosphere. The pattern's origin is a matter of much speculation. Most scientists think it is a standing wave pattern in the atmosphere. Polygonal shapes have been replicated in the laboratory through differential rotation of fluids. Hubble Space Telescope imaging of the south polar region indicates the presence of a jet stream, but no strong polar vortex nor any hexagonal standing wave. NASA reported in November 2006 that Cassini had observed a hurricane-like storm locked to the South Pole that had a clearly defined eye wall. Eye wall clouds had not previously been seen on any planet other than Earth. For example, images from the Galileo spacecraft did not show an eye wall in the Great Red Spot of Jupiter. The South Pole storm may have been present for billions of years. This vortex is comparable to the size of Earth, and it has winds of 550 kilometers per hour. Saturn has an intrinsic magnetic field that has a simple, symmetric shape, a magnetic dipole. Its strength at the equator, 0.2 Gauss, is approximately 1/20th of that of the field around Jupiter and slightly weaker than Earth's magnetic field. As a result, Saturn's magnetosphere is much smaller than Jupiter's. When Voyager 2 entered the magnetosphere, the solar wind pressure was high and the magnetosphere extended only 19 Saturn radii, or 1.1 million kilometers, although it enlarged within several hours and remained so for about 3 days. Most probably, the magnetic field is generated similarly to that of Jupiter by currents in the liquid metallic hydrogen layer called a metallic hydrogen dynamo. This magnetosphere is efficient at deflecting the solar wind particles from the Sun. The moon Titan orbits within the outer part of Saturn's magnetosphere and contributes plasma from the ionized particles in Titan's outer atmosphere. Saturn's magnetosphere, like Earth's, produces aurorae. The average distance between Saturn and the Sun is over 1.4 billion kilometers. With an average orbital speed of 9.68 kilometers per second, it takes Saturn 10,759 Earth days to finish one revolution around the Sun. As a consequence, it forms a near 5-to-2 mean motion resonance with Jupiter. The elliptical orbit of Saturn is inclined 2.48 degrees relative to the orbital plane of the Earth. The perihelion and aphelion distances are, respectively, 9.195 and 9.957 astronomical units on average. The visible features on Saturn rotate at different rates depending on latitude, and multiple rotation periods have been assigned to various regions, just like Jupiter. Astronomers use 3 different systems for specifying the rotation rate of Saturn. System 1 has a period of 10 hours, 14 minutes, and 0 seconds, and encompasses the equatorial zone, the south equatorial belt, and the north equatorial belt. The polar regions are considered to have rotation rates similar to System 1. All other Saturnian latitudes, excluding the north and south polar regions, are indicated as System 2 and have been assigned a rotation period of 10 hours, 38 minutes, and 25.4 seconds. System 3 refers to Saturn's internal rotation rate. Based on radio emissions from the planet detected by Voyager 1 and Voyager 2, System 3 has a rotation period of 10 hours, 39 minutes, and 22.4 seconds. System 3 has largely superseded System 2. A precise value for the rotation period of the interior remains elusive. While approaching Saturn in 2004, Cassini found that the radio rotation period of Saturn had increased appreciably to approximately 10 hours, 45 minutes, and 45 seconds, plus or minus 36 seconds. An estimate of Saturn's rotation, based on a compilation of various measurements from the Cassini, Voyager, and Pioneer probes, is 10 hours, 32 minutes, and 35 seconds. Studies of the planet's C-ring yield a rotation period of 10 hours, 33 minutes, and 38 seconds, with a margin of error. In March 2007, it was found that the variation in radio emissions from the planet did not match Saturn's rotation rate. This variance may be caused by geyser activity on Saturn's moon Enceladus. The water vapor emitted into Saturn's orbit by this activity becomes charged and creates a drag upon Saturn's magnetic field, slowing its rotation slightly relative to the rotation of the planet. An apparent oddity for Saturn is that it does not have any known Trojan asteroids. These are minor planets that orbit the Sun at the stable Lagrangian points, located at 60-degree angles to the planet along its orbit. Trojan asteroids have been discovered for Mars, Jupiter, Uranus, and Neptune. Orbital resonance mechanisms, including secular resonance, are believed to be the cause of the missing Saturnian Trojans. Saturn has 146 known moons, 63 of which have formal names. It is estimated that there are another 100 plus or minus 30 outer irregular moons larger than 3 kilometers in diameter. In addition, there is evidence of dozens to hundreds of moonlets with diameters of 40 to 500 meters in Saturn's rings, which are not considered to be true moons. Titan, the largest moon, comprises more than 90% of the mass in orbit around Saturn, including the rings. Saturn's second largest moon, Rhea, may have a tenuous ring system of its own, along with a tenuous atmosphere. Many of the other moons are small. 131 are less than 50 kilometers in diameter. Traditionally, most of Saturn's moons have been named after titans of Greek mythology. Titan is the only satellite in the solar system with a major atmosphere in which a complex organic chemistry occurs. It is the only satellite with hydrocarbon lakes. On June 6, 2013, scientists at the IAA-CSIC reported the detection of polycyclic aromatic hydrocarbons in the upper atmosphere of Titan, a possible precursor for life. On June 23, 2014, NASA claimed to have strong evidence that nitrogen in the atmosphere of Titan came from materials in the Oort cloud, associated with comets, and not from the materials that formed Saturn in earlier times. Saturn's moon Enceladus, which seems similar in chemical makeup to comets, has often been regarded as a potential habitat for microbial life. Evidence of this possibility includes the satellite's salt-rich particles having an ocean-like composition that indicates most of Enceladus's expelled ice comes from the evaporation of liquid salt water. A 2015 flyby by Cassini through a plume on Enceladus found most of the ingredients to sustain life forms that live by methanogenesis. In April 2014, NASA scientists reported the possible beginning of a new moon within the A-ring, which was imaged by Cassini on April 15, 2013. Saturn is probably best known for the system of planetary rings that makes it visually unique. The rings extend from 6,630 to 120,700 kilometers outward from Saturn's equator and average approximately 20 meters in thickness. They are composed predominantly of water ice with trace amounts of tholin impurities and a peppered coating of approximately 7% amorphous carbon. The particles that make up the rings range in size from specks of dust up to 10 meters. While the other gas giants also have ring systems, Saturn's is the largest and most visible. There is a debate on the age of the rings. One side supports that they are ancient and were created simultaneously with Saturn from the original nebular material, or shortly after the late heavy bombardment. The other side supports that they are much younger, created around 100 million years ago. An MIT research team supporting the latter theory proposed that the rings are remnant of a destroyed moon of Saturn named Chrysalis. Beyond the main rings at a distance of 12 million kilometers from the planet is the sparse Phoebe ring. It is tilted at an angle of 27 degrees to the other rings and, like Phoebe, orbits in retrograde fashion. Some of the moons of Saturn, including Pandora and Prometheus, act as shepherd moons to confine the rings and prevent them from spreading out. Pan and Atlas cause weak linear density waves in Saturn's rings that have yielded more reliable calculations of their masses. Thank you for watching. If you enjoyed this video, don't forget to give it a thumb up and share it with your friends. We'd love to hear your thoughts, so leave a comment below. And if you haven't already, make sure to subscribe to the channel and hit the notification bell so you don't miss any of our future content. See you in the next video.